Hi, welcome to part 3 of lecture 12 on ECE 141 lecture 12 on linear block codes. In this part of the lecture, we will talk about the error correction and error detection capabilities of the aforementioned block codes. So recall in the previous lecture, I showed you examples of linear block codes that have been developed over the past few decades of its existence. Okay. And basically, we established that, again, that if we have a larger minimum Hamming distance, we get better reliability. Okay. And with that, we have less data rate. Okay. So that's a trade-off with using linear block codes. You're using extra bits to detect and correct errors. So if you use extra bits that are not useful, does not give information, then we're reducing the effective data rate. Right. So, okay. Now, let's look at the other side. Aside from transmitting code words, we'll be receiving them. So in the receiver's perspective, you have 2 to the n possible valid code words that you can receive. Okay, and out of all those 2 to the n possible code words, only 2 to the k is valid. Okay, so now how we model the channel is that we can simply model the channel as such, where you have an error vector that adds to the code word and you get a received signal R right here. So this is a higher level abstraction of how we view the channel from before. If you remember, there you go. So if you remember, when we have, let's say, a 4-QAM constellation, our view of the channel, the received signal rather, is still pretty much analog. So your received signal is somewhere within the vicinity of your symbols. Okay, but now when you look at your code words, so in sphere packing, you actually recalibrate or insert a lot of spheres in the vicinity of each symbol. Okay, and you put more possible code words within the vicinity, as you can see here. Okay, so this is your sphere packing representation. Each of this sphere has its own received code word. Okay, but the valid code words are only the ones that are shaded, as you can see. So there's a chance that you will receive a code word from here, from this sphere, and that would mean that your code word is invalid, which means there must be an error in your transmission. Therefore you have detected an error. So you have detected an error. So is it possible to correct that? Well, we'll see that later. So how we model that is, instead of looking at it in an analog representation such as this, your error can just be modeled as some term added to your transmitted code word. Okay, and basically you get an error. So if we try to get its syndrome, right, so we define the syndrome as your received signal multiplied by the parity check matrix transpose. Recall that if you multiply the parity check matrix to code word, you get the 0 vector. So we do that since R is equal to C plus E. So where E represents an error, it's 1 if there is an error in that position, 0 otherwise. So if you substitute your R here, get this expression, you can transpose H of T to both terms, and C times H transposed is equal to 0, as you know. So we're only left with E times H transposed. So, excuse me. So now we are left with this term, and this is only 0 if your error is 0. Okay? Or Okay. Are there any possible cases other than E equals the 0 vector for this E times H transpose to be 0? Recall that any valid code word, okay, when you multiply it to your H transpose, you get 0. So if E is equal to any code word, which is an element of your set of code words, valid code words, if E is a valid code word, then you have an undetectable error. So that is a scenario wherein we are not able to detect an error. And that's the significance of your minimum Hamming distance. If the weight of the error is equal to the minimum Hamming distance, chances are you won't be able to detect the error from your transmitted signal. So that is the importance of minimum distance. Okay, so it defines the correction and detection capability. So instead of maybe if you're not just correcting it, just detecting it, it defines your detection and correction capability of the code. In general, we want a higher minimum Hamming distance. Okay, and those are the examples of codes I've shown you in the previous part of the lecture. Right. So now we define a T-error correcting code such that it can correct any error pattern such that the weight of the error pattern is less than that value. Okay. If we use what we call the nearest neighbor strategy, it can correct basically all errors with the patterns of Hamming weight, all error patterns of Hamming weight W of E, provided that the minimum distance is greater than or equal to 2 times the error correcting capability plus 1. Okay, so let's go back to the illustration earlier, right here. If this is what we received, it's an invalid code word, it's closer. So let me just use another, there you go. So it's closer to this code word than to this code word. Then it must be that your code word that you transmitted, the code word you transmitted must be this instead of this, instead of this, instead of this. Okay? And to do that, the distance between your spheres must be large enough. Okay? At the very least, it should be greater than twice the error correcting capability of the code plus 1. Okay? Greater than or equal. So that is what is illustrated right here in this slide. Okay. So if the distance between the two code words is greater than 2t plus 1, then we can correct the code. Okay? Let's say your receive signal is here or receive code word is here, then we can correct it to the nearest possible c sub I. But if the receive signal is equidistant to both ci and cj, then we cannot correct your receive signal. It could be either of this and you don't know. Okay? So your error correcting code has a minimum number of bit errors it can correct equal to 1/2 of d min minus 1. Okay? So now, how do we correct the error? So from here, we will use the syndrome. Given 2 to the k code word vectors, so that's what the set of valid code words, and r is some receive vector, the decoder has a task of partitioning your space into 2 to the n possible receive vectors into 2 to the k disjoint subsets. So if you look at it in a sphere packing representation, if these 4 spheres represent your valid code words and some other spheres appear because of sphere packing, okay, the decoder must partition these spheres into appropriate regions, there you go, for it to be able to decode your signal. Okay? So the array construction, your 2 to the k code vectors are placed in a row with the all zero code vector as the leftmost element, and some error pattern is picked and placed under your CL, and a second row is formed by adding E2 to each of the remaining code vectors in the first row. It is important that the error pattern chosen as the first element in a row has not previously appeared in the standard array. And you repeat that step until all possible error patterns have been accounted for. Right. So this is the most efficient or standard at the very least of construction of this space by the receiver. So the receiver constructs the reception space, right? Lack of other term to call it, in this way. Okay, so this is its algorithm to construct it, the array construction. Okay, so example. So if you have a 7-tree maximum length code, this is the generator matrix. So solve for the syndrome of each possible code word when there is no error, and there is 1-bit error at the most significant bit. So recall that if you use your linear block code transformation or mapping, you'll get this code words from your set of messages right here, and the syndrome, corresponding syndrome, you try to compute that, you'll get the 0 vector. Okay, so now if we have 1-bit error here, so that's at the the least significant bit rather. So 1-bit error at the least significant bit, then all of this you should add 1. Oh wait, oops, this one is not correct. So let me just correct that. Okay, so this should be 1000000. So that's correct. It's the most significant bit, not the least. All right. So with the most significant bit in error, if you get the syndrome of that, you'll end up with a non-zero syndrome, okay, which indicates that there is an error that is detected. So we have detected an error. So now, if we look at the how to correct the error using the syndrome, you construct an array based on all the possible combinations of errors, okay, from this set, and you create a table where you add your possible error combinations to the all the possible error combinations to each member of your, or each element of your valid code word of the set of valid code words. So like this, okay, and then you identify the received symbol or the received signal. Okay. So we compute the syndrome, S is equal to R times H transpose, and within the coset characterized by the syndrome, you identify the leader. So if you received a signal, you say if your received signal after you get the syndrome, you identify it to be this one. Okay. Then the error pattern must be equal to the coset leader. And if you add that to the received signal, you get your original code word. Okay. Using hard decisions, if you use the maximum likelihood decision rule, then you just need to get the code word that is closest to your received code word. Right? Basically, it's the same as your decoding of your digital modulation schemes, where you create boundaries, okay, between your symbols, and if your received symbol is somewhere maybe here, the symbol that it is closest to that would be the decoded symbol. Okay, so with this, if you take the weight of this, well, that's just basically getting the weight of the syndrome. Okay, so note that H here is the parity check matrix. So the advantage of you doing this is that it's simpler than creating some array that is based on the error patterns. Okay, but it's more computationally expensive compared to this decision rule or error correction. Okay, so also there's a probability that some errors will be undetected, as I've told you earlier. Okay, so that happens when your minimum distance is greater than it's less than rather twice the error correcting capability plus 1. Okay, that just means that if the weight of the error is greater than or equal to the minimum distance, there's a probability that the error will be undetected. Okay, so I've shown you that earlier. Okay, and all for given I bit errors present in the received code words, the number of possible error vectors is n taken I at a time. Okay, and if your error is an element of the set of valid code words, as I've shown earlier, then your error becomes undetected. So for example, let's look at this 5.2 code we talked about in the previous parts. So we have 4 possible messages with 4 possible valid code words. If the error is 01101, which is a valid code word as you see here, then all your received code words, this is R, okay, all your received code words would resemble a code word that is valid. So this is the code word for this one, this is the code word for this one, this is the code word for this one, and this is the code word for this one. Okay, so if you have a 2-bit error, okay, 2-bit error, then you get, okay, this receives the receive symbols or the receive code words. There you go, and you detect errors. So compared to this, where the syndrome is all 0 vectors, but it's an error, you have undetected errors. Okay, so the probability then that your error is undetected is the probability when your E is equal to some code word given all possible code words. Okay, and this can be simplified to here. So AJ is the number of code words with weight J. P raised to J here is the probability of error raised to J possible. Probability of bit error raised to J, and this is this represents the bits that were not in error, and you sum all that, you get the probability of your undetected errors. Okay, so if we add error correction to our digital communication system, so recall that the upper bound of the probability of error is equal to this. Just a note that the probability of having t plus 1 errors is much greater than the probability of having t plus 2 errors. So let's look at that. Right. So when you have a probability of error, if you have 1-bit error per 1 million bits, okay, the probability that there are 2-bit errors in a packet, let's say 2 consecutive errors, the probability that there are 2 consecutive errors is 10 to the minus 12. It's very much shorter, or very much smaller rather, than the probability that there's only 1-bit error. So we'll rely on that concept, and we'll only consider the probability that we have only 1-bit error or t plus 1 errors depending on the error correcting capability of the code. Okay. Because if you have t plus 1 errors, then the code will not be able to correct that. Right. So the probability of error becomes equal to this. And this is only valid if the probability of bit error is much less than 1. So 10 to the minus 6 is very much less than 1. Rule of thumb, this 10 to the minus 2 is already much less than 1. So this term right here simplifies to 1. Okay? So the effective bit error rate after channel coding becomes this equation. So 2t plus 1 here is the number of bit errors that occurred in the most probable scenario. And this n, excuse me, so this is this is the probability of bit error, and this is the probability of code word error. So that's why we divide it by n. So if your error correcting code t is equal to 1, then the probability of bit error is equal to this. Okay. So for example, we have a triple error correcting code with 23 total number of bits in the code word and 12 bits in the message. Let's say that when you transmitted your when you want a probability of bit error to be 10 to the minus 5 in your uncoded and coded cases using BPSK. So note that this 2312 error correcting code, its error correcting capability is t is equal to 3. If we have an uncoded case, then our SNR is 9.6 decibels. Okay, acceptable, maybe. For a coded case, recall, we want a probability of bit error 10 to the minus 5. And we got this equation earlier as an approximation right here. Okay. So the probability of bit error 10 to the minus 5. Since we want to solve for the probability of error for the raw uncoded bits, it's 7.8 times 10 to the minus 3. As you know, this is smaller, or the power needed, the power needed is smaller compared to the power needed here. But note that our SNR, our power used, will be scaled by the data rate. Why? Because we're using 11 extra bits. As you can see, 23 minus 12, 11. We're using 11 extra bits for error correction. But it's pretty much mostly useless in terms of information. Right? That's why we're scaling this EB over N naught by 12 over 23. Okay? Because 11 bits still used power but did not send any data. Alright, so the probability, the SNR per bit becomes 7.5 decibels, which means that we achieved a coding gain of 2.1 decibels. Right, so your 9.6 dB, instead of transmitting 9.6 dB, you only need to transmit 7.5 dB to achieve the same performance. Right, and this is the effect of error correcting codes when we incorporate them into your communication systems. And that's the end of this lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. I'll see you next meeting.